All right, let's get to example 4 now. Student government usually charges $10 per ticket for dances, and they sell 300 tickets. So that's kind of the situation right now. So they did a survey, and it suggested that if the price of the ticket does affect, we all know this, right? Prices affect how much you're willing to pay for something. The more something costs is the less people are able to buy it. That's kind of just reality. The less something costs is the more people are able to buy it. So here's what they found in the survey. A 50 cents change in ticket um, price increase will reduce the number of tickets and vice versa. So it means that if you increase the price by 50 cents, you'll have 20 fewer tickets sold. If you reduce the price by 50 cents, you'll have 20 more tickets sold. That's kind of the way we're saying. Okay. So the fire marshal is saying you have to restrict the crowd to 600 people. So you can't have more than 600. That's your limit. That's as far as you can go with the number of people inside of the building. Of course, these days it's going to be a lot less because with all physical distancing and all that 600 wouldn't work. But anyway, so the student government also has a limit themselves. They're saying if I put in all this work, it's just not worth it if less than 150 people show up. It just doesn't make any sense. So what the objective is now is to see what ticket price to charge in order to maximize your revenue. Right? Now, maximizing revenue is not the same as maximizing profit. Later on, we're going to do a question which talks about maximizing profit. Not today, but we're going to look at a question that maximizes profit. One of the things you need to remember is that as a business person, it's not just revenue that matters, because you could take in $1 million, but your expenses are $2 million, in which case you're losing money. Just a fact of life, right? But this question only focuses on revenue. So we're going to stick to just looking at revenue here. So let's just, to start us off, look at the current situation that they're at, and what if they were to change the price by, let's say, 50 cents? Are they better off, worse off? I just want to sort of make sure we're clear on what's going on here. So right now, so this is the current situation, right? Right? Or let's say this is what they had at their last dance. They were selling the tickets for $10, and there were 300 people who were attending. So if you do the math on that, we're talking about $3,000 worth of revenue. All right, very simple to do that calculation. Nothing complicated there. $10 ticket price, 300 tickets sold, $3,000 is your revenue. Not your cost, but your revenue. I just want to make sure that not your profit, but your revenue. All right. But what if they were to drop the price by, let's say, 50 cents? So now we're talking about, instead of $10, we're now talking about $9.50, right? That's a 50-cent drop in the ticket price. But now we're looking at 320 people coming to the dance, right? Because remember, dropping that price allows you to, yes, you're making less on each ticket. That's true, right? The $10 ticket was bringing in $10, but the $9.50 ticket is only bringing in $9.50. But you're bringing in more people. So right now, I'll just do a quick calculation. I'm not able to do this in my head here. Works out to $3,040. You can confirm that for yourself. So clearly there is some advantage, it seems, to dropping the price, right? How about increasing the price? What if I went up by 50 cents? And now it's $10.50, right? And I'm multiplying that by, now remember, I've increased the price, so it means I'm going to have less people coming. So instead of 300 people, I'm now going to have 280 people. Because remember, every 50 cents change in price causes you to change the number of people by 20. In the real world, I'll be honest with you, it's not as cut and dry as that. But let's just keep going here. So that's 280 multiplied by 1050, and I'm getting 2940. Now, clearly, this one seems to be a better choice than even where we are right now, which is $3,000. But this one looks like it's a bad choice because even though you're getting more per ticket, You just lost 20 people who said, I'm not going to come to your dance if you're going to charge me 10.50. I was even struggling with $10, but you gone up to 10.50, that's I'm out. All right. So clearly, we're still playing around with the numbers, but we haven't yet come up with a more accurate way of judging what the sweet spot is. Where should I actually be charging my price? What's the right price that's going to give me the maximum amount of dollars? So that's where calculus, or when you're in grade 10, quadratics came into play, because this, in fact, does work out to be a quadratic function. So here's how we're going to set this up. Let's let x equal the number of price changes, number of 50 cents, and that thing means number. It's not hashtag in this case. The number of 20 or 50 cents price changes. So what do I mean by that? This first this first 9.50 was a drop of 50 cents. So this would have been a -1 for the x. So if I had a one drop, but in a drop meaning I'm going down, it means that I would have used -1 here as my x for the number of price changes. So one price change of 50 cents. This situation here would have been a +1 because I'm adding 150 cents to my original price. And that's what gives me the x in this particular case. Okay? All right, let me just do a quick check-in because I don't want to leave anybody behind here. Adam, are we good so far? Just want to check in with you. Does that make sense so far? And Alicia, how about you, Alicia? Are we good so far? You can tell I'm looking at this thing alphabetically because those two people have first names at the top of the alphabet. Alicia is good. Okay. So let's come up with something which would represent the price of the product and also the number of people that are coming to the dance. So let's do a price equation, and let's do what should we say now? The attendance equation, or tickets sold. Yeah, let's put tickets. Let's call it tickets. Actually, let's just say tickets. Okay, so price and tickets, number of tickets. So obviously, also I can't spell tickets. Hang on. Sorry, hold on. Okay, so let's think about what the price could be. Now, we started off with a $300 price, right? And what's happening is that this thing we're calling X represents these price changes. Can you tell me what a good equation might look like based on what we have there? So 10 plus X, Cushy says. It's a good idea, right? You saw what I did with the the first ticket price. The first ticket price was $9.50. That was a 50 cents drop. So if X was just -1, that would have been 10 -1. Well, actually, we're not quite finished yet. We have to multiply this by something else. So it's not quite finished. I wouldn't completely agree with 10 plus that. What is missing from that? Not just X, but what? Plus 0.5 times X. There you go. All right. So thank you, Ashfan, and thank you, Taj, and Kushi. I'm sure you agree with what they just put in there. So we have to put the 50 cents, because every time we multiply that 0.5 times an X, that will change the price overall. Okay? All right, so let's get to the number of tickets now. Let's get to the number of tickets. How could I come up with an equation? Let me take you back to the informational question. How can I come up with an equation for the number of tickets that we're selling? Think about how we came up with our equation for price, and give me an equation now for the number of tickets that we would sell. Bearing in mind that we started off at a $300 number of tickets, right? Bear that in mind. What do you say, folks? 300 plus 20x, Adams thinks. Well, I wonder. I would say, okay, look at the correction that Taj made. If we're adding on to the price in the first instance, then we have to minus from the number of tickets. So let's say, so you're on the right track, Adam, but we need to, these two things need to move in opposite directions, minus 20x. So as one goes up, the other one has to go down. We could have, let me just say this, we could have put 10 minus 0.5x, and then we could have put the tickets as 300 plus 20x. So we just have to make sure that we have different directions of the movement. If the ticket price is going up, then the number of tickets being sold has to be going. I'm not sure if I follow why you need to go in opposite direction. Okay, that's that, Adam. Thank you very much. What Adam is doing is exactly what I want the rest of you to be doing. When we were doing this thing over here, let's go back to this. And I'm glad and I always like to start off by looking at a sort of looking at the first, when we're doing the thing with the distance between the two people yesterday, we said, what if it was just 1 hour later? Well, what if it was just one price change? What happened to our ticket price if we decided to drop it by 50 cents? Well, 50 cents means that the original 10 is going down by 50 cents, but the number of people is going up. So the two things are moving in opposite directions. When we increased the ticket price, we went down with the number of people that were attending the dance. And that's why they're moving in opposite directions. And thank you for that question. Okay, so here we have what we're saying represents the ticket price and one that represents the number of tickets. Okay. Can X be anything though? Is there any value of X that is off the table? Let's go back and see if there were any restrictions. It said that the student government doesn't feel it's worth it to go with less than 150. And the fire marshal is saying you can't have a crowd size of over 600. So here's what this means. These tickets, I have to have a condition on the number of tickets where 300 minus 20x has to be greater than 150. We have to solve this scenario first. You're welcome, by the way, Adam. So let's solve this first. So we're saying minus 20x. Remember, we always said we have to look at what is the domain of the function, because if the answer you're getting is outside of the domain, then we're in trouble. We're not really in trouble. We have to look at the borders and see if the borders are where the solution is. So anyway, minus 20x is greater than minus 150, right? And then we're going to divide both sides by 20. So just trying to go down here. There we go. So x must be, hold on, how do I have greater than 150? Yeah, greater than 150, right? So we have to divide both sides. X must be less than, what is 150? By 20, 7.5. Am I doing this right? Hang on, let me just think a second. I must be greater, yeah, 7.5. Okay, sorry, let me see what I'm saying here. 7.5, thank you. Sarah, 300 plus 150. 150 minus 300 is minus 150. Okay, what's the deal? Okay, let's keep going here. All right, so let's go on the other side now. The other side of this is that the same thing, the 300 minus 20x must be, oh, hold on. Yeah, so what, greater than 150, but has to be less than 600. Okay? Less than 600 because of what the fire marshal said. Fire marshal says we're not going to have anything, actually, I should say greater than or equal to, right? Or less than or equal to, rather. And let me see if the other one should have been or equal to as well, with fewer than 150. Yeah, so I guess we could leave it as being greater than 150. It has to be greater than 150. All right, so anyway, so 300 minus 20x, we'll do the same thing here. Minus 20x is less than or equal to 300. and therefore x has to be greater than or equal to minus 150. Hope I got that right. Somehow it doesn't sound right, but anyway. All right, so what we're saying is, based on, is that not 150? 15. Yeah, you're right. Thank you. Thank you very much. It is 15. Must be greater than 15. So looks like we're saying that our x, our domain, is from anywhere from minus 15 anywhere up to 7.5. And I'm going to put a round on this one. All right, to include that. Thank you. Thank you for the correction, Kushi. All right. So now we know the limits of our x. X has to be somewhere between. So either you can drop it down up to that point or raise it up to this point. Beyond that, this is not going to work. All right. Excuse me. So let's now see if we can come up with an equation for the actual revenue. Can anybody suggest what our revenue is? We have an equation for price, we have an equation for tickets. What's the revenue equation that we should be putting together here? Can anybody help me with the revenue equation? Revenue is equal to, let's use R for revenue. R of X, I should say. Let's call it an R of X equation. Okay, so you're going to take the ticket price and multiply it by the number of tickets. Makes perfect sense. So we're going to take the two things together, which is a 300 minus 20x, and multiply that by the 10 plus 0.5x. Okay, price times tickets equals revenue. I'm just reading it straight from the chat. Kushi has spoken. All right, price of the ticket, and Tej has spoken as well. Excellent. Anika has also put the equation in. Is everybody okay with that so far? Let me go down the alphabet here. Actually, I'm going to go to the bottom of the alphabet. How about Zach? Zach, how about you? Are you with me so far on that? All right, does this all make sense? If it doesn't, you should be like Adam. You should say, hey, Mr. Kamak, I'm not so sure about this. What can we go back and talk some more? But Zach, how about you? You're good? It does. Okay. All right. So here's our R of X, and this is what we're trying to maximize here. And I think we know that if we're trying to maximize something, that we're going to need a derivative. So we could use the product law. That's possible because it's right now set up as a product. Or we could multiply it out so that it is a straight polynomial and we don't have to think about things like the product law. My preference is to put this as just a straight polynomial. So 300 times 10 would be 3,000. 300 times 0.5 would be plus 150x. Minus 20 times that would be minus 200x. Y'all got to make sure I'm doing this right here. Minus 10x squared. Okay, and I'm going to sort of fix this up a little bit. So minus 10x squared. And then I'm going to say minus 50x. And then plus 3,000. Okay. All right. So hopefully, so far, so good. Vanessa, how about you? Did I do anything there that didn't make sense? What do you think? You're okay with that so far? Great. All right. I hope I didn't make any mistakes there. 150 minus 200 minus, okay, right. And it's good that this function seems to be a quadratic which opens down, because if it opens down, it probably has a max point somewhere. So that kind of makes sense. That minus 10 in the front is what we'd expect if this was a quadratic that had a maximum on it. So let's now find our R prime of x. That's equal to minus 20x minus 50. Okay. And then we're going to do what with this derivative again? Now, what comes next with that derivative? Anybody remember what this looks like when we have a derivative and we're trying to maximize a function? What do we do with our derivative? We have our derivative. What comes next? Help me out, folks. I'm struggling here. I don't know what to do. We set it equal to 0. Thank you. So that means that minus 20x minus 50 is equal to 0, which means that minus 20x is equal to 50, and therefore x is equal to 50 over minus 20, which for me is minus 2.5. All right, so now we're able to answer the question. Let's see what the question was, though. Question was, what ticket price should be set to maximize the revenue, right? Well, first of all, we should ask ourselves, is this number acceptable? We have minus 2.5. We said the domain was between minus 15 and 7.5. So we're good. All right, we had a pretty wide berth to work with here. Minus 15 to 7.5 is okay. We can work with that. All right, and we worked out minus 2.5. So now we should do what? Because the question asked us for the price, right? Didn't ask us for the revenue, asked us for the price. What price should we what price should we set to maximize the revenue? Is there something here that can help us to go to that next stage, which is the answer we're looking for, by the way? Can anybody point me in the right direction for that? Use a price equation. Thank you, Adam. We got a price equation right there, 10 plus 0.5x. So let's see if we can do that. So price is equal to 10 plus 0.5 times minus minus 2.5. So it sounds to me like we're about to give these kids a break on the price, because we're using a negative here, which suggests a price reduction. And what price is it working out to be? Sorry, I'm so late, Shashti says. The meet kept bringing me to a blank page. Okay, not sure why that is. All right, but I will mark you as being here at any rate. And which link were you using? Which link were you using? Are you using the link that's on the D2L, by the way, Shashti? Because I'm just concerned about that. Why are you getting a blank page? Same one on the D2L? Okay, not sure, but anyways, eventually working. So that's the most important thing. All right. By the way, I need to speak to both yourself and Thomas a little later on in the class. Okay, just putting that out there right now. Can anybody give me Can anybody give me the actual price that we're looking at here? 875 is what I'm hearing, and that's clearly in dollars. So if the question was asking what the revenue is, I'm sure that we'd understand how to do that. Right? That just puts it back into the revenue equation, and then we'd have an answer. And if the question was, how many people are we talking about? I'm sure we could answer that as well. We put that into the number of tickets equation. And because we already defined the domain, we know that the number of tickets should be somewhere between that 150 and 600, right? It shouldn't be that it's less than 150. It should be that it is greater than 600. But just out of curiosity, what are we getting if we put that 2.5 minus 2.5 into the number of tickets equation? So this equation right here. Could somebody work that out for me, please? So 300 minus 20 times the 2.5. How many people are we talking about? I'm just curious. I mean, I know I could put calculate for myself, but could you all, with your calculators, work that out for us, please? And let's just confirm for ourselves that we still are within that 150 to 600 thing that we're talking about. How many people are we talking about for the number of tickets that we're selling here? 350. Thank you very much. So clearly, we're selling more than 150. Clearly, we're not yet bursting at the seams so that the fire marshal is going to come and shut things down. All right. What are we calculating? Sorry, Kashaf. The question, thanks for the question. The question was, I was asking something the question wasn't actually asking. I was asking you to tell me how many people we were talking about, because we wanted to kind of make sure that we didn't, we didn't have the fire marshal concern because we're over 600, and we weren't wasting our time because the government had said that we're not going to do the dance unless 150 people. There's no point to that. So what I asked people to do was to work out how many people would be coming to the dance if we were selling the tickets at that price, and that's what they were calculating, Kashaf. Does that answer your question? Okay, so that's where that came from. But the question, though, let me just answer the question. All right, formally, the the price should be. I always like to put that statement at the end. 875 to maximize revenue. Maximize revenue. All right, I'll just put REV for short. Okay, so that's it, folks. Really wasn't that difficult a question. When you did, I'll tell you what you did back in grade 10. What you did back in grade 10 is when you had the function set up like this, you may not remember this, because it was you had two zeros from these two things here. What you did is, and you might find this easy as a matter of fact, is you said, okay, so these are my two x-intercepts. I know that the vertex is going to be between those two x-intercepts. So you set each of these equal to 0, and then you found half of that, or you found the midpoint between those two. You might remember this from grade 10. And then you said, okay, that means that's my x value that's going to create that's going to be at my maximum. And then you go from there. So if you were to take each of these and set them equal to 0, add and up and divide by 2, you'd get the same answer of x as being minus 2.5. All right? Just saying. Just sort of bring it back to your grade 10 experience. All right. A slightly more challenging question. All right, hold your breath, folks. Take a deep breath, and let's see if we can sink our teeth into this one. A cylindrical container needs to be made so it will hold a liter of liquid. For a quick note here, I say that 1 liter, I'm sure a lot of you know this already, that 1 liter is 1,000 centimeters cubed. All right, it's a volume. So when you buy gas, you buy it in liters in Canada anyway. In the States, it's bought in gallons, but it's the same thing as 1,000 centimeters cubed, which is actually 10 centimeters by 10 centimeters by 10 centimeters. If you want to think of it in terms of the dimensions of a box, it's a box with 10 centimeters on each side, and you take 10 times 10 times 10, so you get 1,000. So that's what a liter is. Anyway, so this container needs to hold a liter of liquid, chemical. It's going to be stored in a cupboard on a shelf that's 12 centimeters by 30 centimeters with a height clearance of 12. So I've tried to sort of show you what that looks like. So here's a cylinder that we're trying to fit into this shelf cupboard, into this cupboard. And the dimensions are as shown, 12 by 12 by 30. So clearly, this thing cannot exceed the dimensions of the cupboard, all right? The cupboard is the limit right there. All right, so the height of the cupboard is 12. It's a 12 by 30 at the base, so 12 by 30 at the base, and this has to fit inside of that. So think about that for a minute. The material used to make the cylinder are different qualities and costs. The bottom must be cost 60 cents per centimeter squared. The bottom is an area, right? It's a surface area. The top is made with the cheapest glass, and that's 30 cents per centimeter squared. That's also an area. The body was sometimes just called the lateral surface area of this cylinder. So around the sides would be 40 cents per centimeter cubed. So if it is possible to make a cylinder that meets all these criteria, what should be its dimensions in order for it to be made most inexpensively? So what we're looking here for is a minimum cost, right? That's what we're looking for. We're not trying to maximize anything. It's called optimization. And optimization sometimes is what's the least, what's the minimum? The question we did before was the maximum revenue. Now we're looking for the minimum cost. And we're given some specific cost elements in this. 60 cents for the bottom, 30 cents for the top, 40 cents for the lateral surface area. Because that's what the material costs. And we're trying to see if we can break that cost down to, or bring that cost down to as little as possible, and also fit inside of this thing here, right? So this thing cannot be bigger than this, right? So how is this going to affect the dimensions? Let me remind you of something, by the way, that the volume of a, I'm going to put some equations down here. The volume of a cylinder is pi r squared height, and the surface area is 2 pi r squared plus 2 pi r h. So it's important for us to remember those formulas for volume and surface area because both are involved here, right? We are looking for a particular volume, a liter, and we have to cover the outside of this cylinder with material. So we're talking surface area as well. So we're dealing with both at the same time, volume and surface area. All right. And at the same time, we're trying to see if we can minimize costs. So it's an engineering problem. For those of you who are thinking of going into engineering, this is an engineering problem, right? How do you sort of define the dimensions that are going to meet all of these specifications? So first thing we need to ask ourselves is this. What kind of restrictions do we have on this particular product, this cylinder, right? What is the maximum R and what is the maximum H for this product? Can anybody sort of help me out with that, right? Look at what we have to fit this into. We have to fit it inside of this box right here, right? How is that limiting the R? How is that limiting the H? Can you give me some guidance on that, please? Right? I've even given you a diagram to help you out here. So this guy here needs to fit inside of that. So the height can be no more than 12. Thank you, Kushi. That's absolutely true. We can't have a height that's more than 12. What else is a restriction? What other restriction do we have apart from that? So that is it only the height that's going to be the limiting factor here? Kushi is right, by the way. She's absolutely right. Is there any other restriction on this apart from the height? Is there a restriction on the radius? Okay, you say W has to be. What do you mean by W? Tell me what you mean by W, Adam. The diameter. Ah, okay. Let me see if I can go back here a bit. Okay, so Adam is saying W, and Kushi's kind of refining that a bit. The diameter 30. I'm not sure if 30 is the right thing though. Right? Why did width? Okay. Um, the depth is 12. Okay, good. That's the when you say depth, are you talking about the height, Sarah? I'm trying to see what you mean by the depth. Is that what you're talking about? The height of the thing can be more than 12? Because yes, I would agree with that, absolutely. No, no, I don't have to start with anything. We're good. Um, but but is there any restriction on the radius, is what I'm asking. The radius. Is there anything that limits the radius of this thing? Right? I'm not sure what you mean by depth. Though. When you say depth, I think you might be talking about the height. Is that what Sarah's talking about, by the way? Okay. And yes, you're right. Right? I think it was, yeah, yeah. I think it was Kushi was mentioning that before, that the height could be no more than 12. I agree. How about the radius, though? Does the radius have any limitation on it? Has to be less than 15, you're thinking? That's interesting that you say that. Think about the fact that this is a 30 by 12, right? So I don't think you should be focusing on that 30 at all. Because remember that this thing is round. Okay, Sarah? It's round. So look at what Adam just says. It has to be no more than 6 for the radius. All right? You can't have a radius of 30, or let's say diameter then, right? Or 15. I guess you're using 15, because the problem is that it might fit in one direction but not fit in the other. It's round. So right now, I'm saying that the R must be less than or equal to 6. That's the first thing we have to accept. Can we all accept that? That the R has to be less than or equal to 6. Okay, so do we adjust according to the lesson? Oh, yes, absolutely. You think just think about this a minute, right? If something is round, then it means that it will if one side of this is 12, right? One side of this box that is going in, I'm just going to point to the box here. If one side of the box is 12, then I can't fit anything in this thing which is bigger than 12 in diameter. Do you see what I'm saying, Kushi? If this thing has a bigger diameter than 12, then I'm in trouble. Right, because it's round. So it's so in every direction, it needs that to be the distance across here has to be 12. If I made it more than that, then it's not going to fit in this direction, right? So this is the thing that's most limiting. So it doesn't matter how long it is. It more matters what the shortest distance is what we're saying. The shortest distance here is a 12, so that's going to limit how much of this thing we can put inside here. All right, so everybody, I want to make sure that everybody is on the same page with me with this so far. Tomalea, how about you? I don't want to leave anybody behind here. Tomalea, are you with us on? Okay, great. So I'm saying that R has to be less than 6. As far as the height is concerned, let's do this. Let's see if we can come up with an R which relates to that. So I'm going to say, excuse me. Now remember, this thing has to be able to hold 1,000 centimeters cubed. So I'm gonna do this. I'm gonna say that V is 1,000 is equal to pi r squared times, and by the way, remember that we said that 12 was the maximum height of this thing. Pi r squared 12 is the maximum height of this thing. Let's solve for r and see what the lower limit of the r is in this case. So pi r squared times height, and we're putting the height as being 12. We mentioned when he mentioned that before, that the height of this thing could be no more than 12. And therefore, r squared is equal to 1,000 divided by 12 pi. And therefore, r is equal to the square root of, because this thing has to be 1,000, remember? A square root of 1,000 over 12 pi. Can somebody help me out with that, please, on your calculator? Can you put that all in and tell me what you're getting? The square root is on everything. So 1,000 divided by 12 pi, and the square root of that, 5.15. Thank you very much. So that's the kind of other limit that we have on our, thank you, Ashland, by the way. That's the other limit that we have on R. If it's going to be 1,000, and if the height cannot be no more than 12, it means that my R has to be at least 5.15. Because if you go below that, you're not going to get that 1,000 anymore, right? So I'm going to define my domain as being the following. Domain of this function, the domain of this situation is that R has to be somewhere between 5.15 and 6. It's a very narrow range, by the way, right? Very, very narrow range. So why must be less than 6? We talked about that before. Has to be less than 6 because we have to look at the shortest distance that this box represents in terms of its the base of the box, and that has a length of 12. And we're thinking about radius. Radius is half of the diameter. The diameter of the cylinder can be no more than 12, and that's a very tight fit, by the way. And the radius that corresponds to a diameter of 12 will be half of that, which is 6. So 6 would be kind of the upper limit on that. And we're saying if you want to get this 1,000 as the sort of volume of this thing, then working backwards with a height of 12, which is the maximum height, then we're getting that the R can be no lower than 5.15 to give us this volume of 1,000. Okay, so 5.15 to 6 is kind of where that's the sweet spot right there. Okay, now let's go back and look at our situation here. Volume is given by this equation. Surface area is given by this equation. We have to somehow come to an equation for surface area, which also brings into account all of these costs. Let's leave the costs out for now. Let me come down here, and here's my surface area equation, right? Just write that again. Surface area is equal to 2 pi r squared plus 2 pi r h. Now, is there some relationship between the volume and the height? Obviously there is, because we have an equation here that says that the volume is equal to pi r squared h. So if I were to take that equation and isolate the h, I'd say that h, just using this thing up here, is equal to v divided by pi r squared. And also, we know the volume that we're trying to find is 1,000. So it's 1,000 divided by pi r squared. Let me just make sure everybody is following me what I'm doing here. And my volume needs to be 1,000. I'm just trying to isolate for that h, because I want to put that h back into this formula here. It's kind of like a composition of functions. I want to be able to put this equation in terms of surface area. So I'm putting the 1,000 here is equal to the pi r squared times h. And therefore, h is equal to 1,000 over pi r squared. Why am I saying 1,000? Because 1,000, remember, was the volume that we need for this particular situation. This is the required volume. So if I isolate h, I'm going to have this. I'm going to rewrite this surface area now as 2 pi r squared plus 2 pi r. And then I'm going to plug this thing in. 1,000 for the h over pi r squared. Okay, that's going to give me my surface area. And I can simplify this a little bit. I mean, we have put this over 1 if that helps you to see why I can simplify it. That should mean that my surface area should be equal to the 2 pi r squared. This r will cancel out with one of these r's here, leaving with r to the power of 1. This pi cancels out with that pi right there. So what I'm left with is 2 times 1,000, which is 2,000, over r. All right? This represents my function, pi r squared, sorry. This represents my function that we need to minimize in order to be, and it's only in terms of r, that we need to minimize in order to be able to figure out what radius will give us that 1,000 volume, right? Given the restrictions. All the restrictions are built in already. We built it in to get the upper limit. We built it in to get the lower limit of this. And so what we're trying to do now is see how we can solve for r here. Not r is not solve for r, but to maximize the surface area. Actually, not maximize. I'm saying that wrong. It's minimize the surface area given those restrictions. But we have to go a little further, unfortunately. We got some costs. Hope I'm not, and I can stop and sort of go over anything that anybody's not comfortable with. So please let me know if where we are so far isn't making any sense. All right. Shashti, you joined late, so I'm hoping that we haven't gone too far ahead. You hopefully have read the question. Let me give you a little chance to look at that question. And all we've done so far, Shashti, is we have, well, first of all, we spelled out what the formula was for volume and surface area. And we said that if we're going to fit, Shashti, you're there with us, right? You're listening to all of this. You're making sure that you're trying to piece together. I know you came in late, but you're following what I'm saying here. You're listening carefully. Shashti, are you there still? Where's Shashti? What happened to Shashti? She's still with us? Not there. Oh, well, anyway. All right, so let me just continue then. Let me just continue. So here's where we are so far. And if anybody else, I was calling out to Shashti, not hearing her, but if anybody else isn't comfortable with any part of what we've done so far, please let me know so we can stop and sort of review it. But here's where we are so far. This, though, doesn't bring in the cost element yet, right? We haven't brought in the fact that the top costs, let's just see, the bottom costs 60 cents per centimeter squared, the top costs 30 cents per centimeter squared, the body costs 40 cents per centimeter squared. We haven't brought that in yet. We need to bring that in now. Can anybody suggest how we might bring that into the equation? If we just solve this now, this will be treating everything as having the same cost. The top and the bottom, the material for everything is the same. So if we didn't do anything else and just went ahead and derived this, then we would end up with an R that makes the assumption that all costs are the same. We could do that, right? But we get a different answer. So we're trying to see if we can incorporate the actual costs. Well, let me put it to you this way. You probably would recognize that this pi r squared doubled represents the top and the bottom of the cylinder. So if you look at the cylinder, let me go back and show the cylinder again. The cylinder has a circular top and a circular bottom. The area of a circle is pi r squared. And the reason we have two pi r squareds in the formula is because we're taking the areas of both of these two together and adding them up. That's why we have 2 pi r squared. This part of the function here actually represents the lateral surface area around the sides. So this is the lateral surface area, and this part here represents the area of the top, area of the bottom. So we can separate them since we have different costs for the top and for the bottom. We can separate this 2 pi r squared into pi r squared and pi r squared. 1 pi r squared at 60 cents and 1 pi r squared at 30 cents. And that's exactly what I'm going to do. So I'm going to say that the form that we're looking for, this surface area, I'm going to say call it S of X now. So for S for surface area. I'm going to say one of them is 0.3 times pi r squared. And the other one I'm going to say was, I think it was 60 cents. Yeah, 60 and 30. So the other one is 40 cents. And then I'm going to say 0.6 times pi r squared. And then I'm going to say that the lateral surface area, right, which is this 200 over r, that's what is reduced down to. I'm going to say that I'm going to multiply by, I think it was 40 cents, 0.4 times 2000 over r. All right. I hope I haven't lost anybody, right? Please let me know. So I'm just going to simplify this a little bit and say that my S of X, these are like terms. I'm going to call this 0.9 pi r squared, right? That's a pi r squared and a pi r squared. It's a 0.3 and a 0.6, so 0.9. I'm going to multiply the 0.4 times the 2000. So I'm going to think this is 800 over r. All right. Again, I know it's a lot I'm throwing at you, and I want to make sure I'm not leaving anybody behind. All right. Sarah, how about you? Sarah Warner, are you there with us? And does that make sense? Sarah, let me know whether you're following me, please. You are. Okay, good. And is Shashti back with us now? Shashti, I'm calling out for you. Where are you? You joined us a couple of minutes ago and now you've disappeared. Where are you? Shashti, are you there? Not there. Okay, so in the time that we have left, let's try to see if we can find a derivative. Because now we're at the point where we have a function which gives us the surface area for any value of r, but now we're trying to find the value of r that gives us the minimum. So we're going to find the S prime of x, and that's obviously going to be equal to 1.8 pi r. Think of this as being r to the minus 1, so minus 800 r to the minus 2. Okay, remember that this 800 over r is the same thing as saying 800 times r to the minus 1. Okay, so let's write it this way. 1.8 pi r minus 800 over r squared. All right. So how can I set this equal to 0 and solve it? Well, it's not that hard. I mean, I could find a common denominator and all of that, but it's not that hard for me to do that at all. Because if this minus this is equal to 0, right? So 1.8 pi r minus 800 over r squared is equal to 0. And I could just make this equal to each other. I don't have to find a common denominator or anything like that. So I'm just going to say that 1.8 pi r is equal to 800 over r squared. So wait, why is it r to the power of, okay, all right. Okay, so let's do a little aside here. Thank you very much for the question, Sarah. Let's do a little aside here. Think of this 800 over r. I'm going to put it in red, right in the corner right here. Instead of saying 800 over r, I'm going to say 800 times r to the minus 1. Would you accept that that's a same? Oh, okay, derivative. And then when I do the derivative, you would get the minus and so on. So you're okay now, Sarah. Okay. All right. Thank you very much, Sarah. You know, Adam and Sarah really make it's, you know, just tells me that people are engaged and that's important. So I'm really happy for students who are doing exactly what Sarah and Adam have been doing. And I know others have been doing the same thing as well. So I'm not just calling those names and saying that those are the only people. That's not true at all. Okay, so thank you very much for the question. So how do we solve this? Is the question. It's now equal to 0. What do we do now? Can anybody help me out? So 1.8 pi r is equal to 800 over r squared. What do we do now? How do I solve for r? Right? What's the algebraic principle that we would use at this point, folks? Right? What's the r that's going to make this magic happen? What do we do? Nobody? Anybody? Silence in the court. Isolate for r. Yes, good. How do we do that? Put in the value for pi. Okay, try. Richard, look at what Richard just said. Cross multiply. That's perfect. Okay, so if you saw what Cushy had, I'm pretty sure that's on the right track. But let's do it a little bit more slowly. So I'm going to say 1.8. I'm afraid to touch that eraser. 1.8 pi r multiplied by r squared is equal to 800. That's the cross multiplication principle. I'm going to have r cubed on this side is equal to 800 divided by 1.8 pi. And of course, that would mean that r should be equal to the cube root of 800 over 1.8 pi. All right. R.I.P. Ashman said. I'm not sure if that refers to me or the smartboard. I don't really know. But anyway, so what's my R, right? Can you figure out what the R is from that? So Cushy was right all along, right? By the way, don't use 3.14 for pi. Please use a pi key on your calculator. Just making sure you do that. 11.89. Whoa, that's a pretty big number. The cube root. Using cube root, Kushi, you sure you're using cube root and not square root? 5.2, you did square. Okay, that's all right. All right. All right. So anyway, 5.21 sounds like a much better number. And why that's a better number is because when we were doing all of our restrictions earlier on, if you remember, we said that our R had to be somewhere between 5.15 and 6. So this answer actually makes perfect sense. This, of course, is in centimeters. So it sounds like we have, that's okay, Kushi. It sounds like we've hit the, let's see if we've answered the question though, because sometimes I forget what the question is when I'm doing this. If it's possible to make a cylinder, we've done that. What should be the dimensions in order for it to be the most inexpensive made? Okay, so this is the radius that we're talking about here, right? The radius is this 5.21. What would be our height, right? How do we get our height? Well, folks, we had a height equation all along. Right? When we made that substitution, we said that the height was equal to the 1,000 over the pi r squared. So we really only need to put that value of r into that function. So 1,000, this is going to give us that 1,000 volume that we wanted. Pi times the 5.21 squared. Okay. Can somebody tell me what that number is, please? Make sure to use your brackets when you're dividing, and then we're going to take our break after that. We have one other question to do. Can somebody work this out for us, please? Anybody? What is this working out to be? 1,000 over pi times 5.21. 11.72. Thank you very much. I'm going to take it that that is correct. 11.72 in centimeters. So let me just put a bow on this now. I always like to answer with a statement, which is what I'm expecting you to do. So what should be dimensions? So the dimensions of the cylinder, and this is going to make sure that all of the costs are taken into consideration. Everything that was given in the question is taken into account. So the cylinder, the dimensions of the cylinder and this is the cylinder that gives you the minimum surface area, by the way, would be radius of 5.21 and height equals 11.72. By the way, bear in mind that the height could not be more than 12, right? So you can see that because we paid attention to all of those restrictions, that we're within this height limitation of the 12 centimeters. So this thing is going to fit fine, right? It gives us a 1,000 centimeters cubed. It gives us an R, which is less than what this restriction is here. We couldn't go more than an R of 6, remember, because the smallest dimension was 12, right? That's one dimension of the base was 12. We're getting 5.2 something or the other. So this is going to fit fine, and it's going to give us our 1,000. And we're going to have the least cost of the material that we need to cover this surface area. Okay, so we only need to do one more question, and then we're going to go through the questions that we had on the pop quiz, and then I'm going to try, if we have time, then I'm going to try that group activity that we talked about. All right then, so we are back in business. So we finished this question. Hopefully everybody followed that, and it's one of the more challenging questions. I'll be the first person to admit that, right? But there's one more. Similar, but I think easier. Hopefully. Anyway, easier. So this one actually came from the textbook. A net enclosure for practicing golf shots is open at one end. So this end in the front here that I'm pointing to is open. This is where you enter this, it's almost like a tunnel, and do your golfing. I don't know if any of you are golf enthusiasts in the room, but that's where you enter and you can start putting inside here. The rest of this thing is enclosed. The top is enclosed, the bottom is enclosed, the back, the sides, and the bottom. Well, the ground, of course, is, well, the ground is the ground. Excuse me. Okay, so find the dimensions that will minimize the amount of netting needed. So kind of similar, right? But you'll be minimizing again. Give a volume of 144 meters squared. That shouldn't be squared. That should be cubed, shouldn't it? Yeah. Anyway, netting is required only on the sides, the top, and the far end. So what we're saying is that this netting should be here on this surface here, that surface there, that surface there, and on the back, right, somewhere around there, right? So we're really trying to cover 4 surfaces, right? So the sides, so here, 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 not the bottom, right? The top, right on top here, and the far end, right? So the ball doesn't shoot out the back. So that's what we are dealing with. Luckily for us, this one doesn't involve as much of the stuff to do with, cost of the top as opposed to the back and all that good stuff. So it's a little bit more straightforward, and that's why I thought we would try it. Similar, but not quite the same. All right. So we're talking about volume of 144, and we're talking about minimizing surface area. So let's start off by talking about how we would get the volume of this particular shape. And they give you dimensions. This is an X, and a Y. How would I calculate the volume of this, what is this, enclosure, this net enclosure, right? How would I do that, right? Help me out here, folks. How would I calculate that volume? So I would take x length times width times height and equal, which translates to x times, right? So let's say x squared times y. That's what we're saying, right? And also that volume needs to be 144. Right? That's the volume that we're trying to get here, which would mean that just like we did the last time, that we can isolate the y and call it 144 over x squared. All right? That hopefully makes sense so far. Now let's look at the surface area. Let's come up with a formula for surface area. The surface area of this, how many surfaces are we covering here? Let me start with that. Can anybody count all the surfaces that we're covering and tell me how many you see? right? And then we're going to come up with a formula for each one. How many surfaces do you see being covered here? Count them, please. Look at the diagram, you count them. I've kind of almost given it away all the same. With the netting, yes, yes, Adam, it's 4. And I gave it away because I put all the dots there for you, so I certainly gave it away. What about the sides then? What would be, how do you calculate the surface area of the sides? So these sides here, so let me circle the ones that I'm talking about. So what is this, what are these areas here? How do you get those surface areas? Those would be x times y, absolutely, absolutely. So let's say 3xy, because can we agree that all of them would be, let's just make sure though, that's y there. No, that's not true at all. That's not true. Let me take that back. Let me take that back. The top would be x there. No, it would be x times y. No, that's right. 3 times x times y. Could we agree on that, folks? That every single one of those has an x and a y as an area calculation. Yes, so 3xy. Okay, so I'm taking it back. I was wondering whether the top was going to be different, but it's not because it's a square on one end. Plus, what else do we know about that? What about the back? What's the area of the back? The x squared. Good. Okay. Okay, that's good. So no, why don't we put these things together? It's like a composite function. Why don't we put these two together to see if we can come up with the surface area formula that gives us this 144 right there, all right? And of course, we would do that by putting this 144 over x squared in place of the y in our surface area formula. We'll use s again of x. So 3x times 144 over x squared plus x squared. All right? See how much easier this one is? After we went through that one first, I probably should have done it in reverse order. I probably should have done this one first and then done the other one. All right. So let's see if we can simplify this now. So 3 times 144. Where's my calculator here? Not everything I can do in my head, folks. I'm not that good. Okay. 3 times 144 is 432. So one of these x's cancels out that x at the bottom. So 432 over x plus x squared. Can we agree? Thank you, Kushi. Can we agree on that as our function after you reduce out the x's? 432 over it. Thank you. Thank you, Adam. Okay. All right. Stephen, are we good so far? Stephen, are you with us so far? Anika says you got that too. Perfect. Stephen, where's Stephen at? Perfect. Makes sense. Okay. So now we can get, this is our s of x formula function. Now we can try to get our s prime of x function. And remember, this is 432 over x, so hopefully this should look like what we did the last time. This should be minus 432 x to the minus 2 plus 2x. Tell me if we're good with that, right? This is the same thing as 432 times x to the minus 1, so that would be minus 432 x to the minus 2, all right? That's my S of x formula. And I'm going to rewrite this as minus 432 over x squared plus 2x. Now, we just did one like this. Can I ask you to finish this up and tell me what value of x this works out to be? All right, let me take a few minutes, stop. Gonna just let you do some work now. And I'm going to call on one of you in a minute. Go back and look at the previous page if you need to. And I can certainly scroll back to that if you need me to. Does anybody need me to go back to the previous page to see what we did there? Or do you think you can all do this without me doing that? Right? Because I'm going to be asking one of you for the answers in a minute. We just did one very similar to that. So it shouldn't be too difficult. Anybody need, can we go back? We sure can, Sarah. Absolutely can do that. So when we got to down here, right? We said that this was the derivative here, right? and then we set it equal to 0. When we set it equal to 0, we cross multiplied. We ended up with this, and then we solve for r. Okay. And so Sarah and Sarah, are you both okay with that? Does that help you out there? It does? Okay, great. So let me come back to this page now, and let's see if we can get an answer for this. I'll give you another couple seconds to get that done. So y'all know I'm pulling up the wheel now, right? Y'all know that. That won't be a surprise to anybody if they heard that the wheel was coming out. Nobody's gonna be shocked when they hear that the wheel is making an appearance, right? And the wheel is spinning right now, and let's see who is the lucky person who gets the prize for the weekend. Ah, okay. Adam, you're up. The wheel has spoken. You have an answer for us, Adam? Still, okay. That's okay. Let's go through it one step at a time then. Wheel of That's funny. That is so funny, Richard. Danny will tell you that it used to be called the Wheel of Anxiety at one point, but I guess it has a new name now. Anyway, so let's go back. Let's go back to not just Adam, but everybody else, right? You know, Adam, you're ready to go with us, and everybody else who's not there yet. That we need to set this thing equal to 0, right, Adam? Okay, so let's do that. Let's set it equal to 0. Grabbing my stylus here. So minus 432 over x squared plus 2x is equal to 0. So if it's equal to 0, what might be a good next step you're thinking if it's equal to 0? I'm trying to isolate x eventually. What might be a good next step? Trying to get to that x eventually. All right, can anybody give him a little push start? Anybody, you can unmute. I mean, you can just talk to the class. Sometimes that's so much easier. All right. Go ahead. LCM. Oh, are you thinking about trying to put it into one fraction? Is that what you're thinking, Kushi? But that's certainly possible as well. That's one way to do it. But just bringing a fraction over, Fernando, I think is easier. You could find a common denominator. Yes, you could. Absolutely could. But I think it's easier to add this 432 over x squared onto the right-hand side. So 2x is equal to 432 over x squared. Okay? All right. So, Adam, how about you? When you see that, does that suggest what the next steps should be? Does it kind of give you a, okay, what would you do at this point? If you see 2x is times by on both sides, absolutely. So it would be 2x cubed is equal to 432. All right. So finish that up and give us your answer now, please. Finish up that equation and give us an answer. What is x equal to in that case? Think back to what we did on the previous question. And then once you put your answer in, we'll hear from other people as to whether they agree with you or not. Let's hear from you first. The Wheel of Misfortune. What a name to give my precious wheel. All right. Just I can't believe the names you're 6 is that what everybody got? It's scary, is that right? When anyway. All right, so everybody has got 6. Let me just I'll leave the wheel out of this for now. So x is equal to 6 is right. Yeah. So let's answer the question. By the way, we haven't answered the question yet. Let me go back and look at the question. Let's see now. Find the dimensions that will minimize the amount of netting needed. So if x is 6, Do we know what y is? Well, we had an equation for y. It's right here. If this thing is going to be 144, thank goodness. Okay. If this thing is going to be 144, and this is wrong, it's with meters cubed, by the way, then this should be the way to find our y, 144 over the x squared. So here's our next step. My y is equal to the 144 divided by 6 squared. And what does that work out to be? Not just Adam. Y is equal to 4, I'm hearing. That's what everybody else is saying. Taja's agreed with Ashvan and Adam. Okay. So now we can put a statement which says that let's see how we say this now. The dimensions. The height. Oh, let me just think for a second now. The front entrance. Okay, the length and width of the base would be 4 times 6. Let me put it that way. The length, or 6 times 4, and width of the base would be 6 meters by 4 meters. The height would be the x again, which is 6 meters. Okay. So that's how I would answer that question. And folks, that was quite a marathon. And in fact, all we have left now is a success criteria.